Sorry about that, I just meant to pause, but I accidentally hit stop, so I have to do this in 2 videos. So, I want to clarify first what this means. So this is an identity with m rows or columns, the identity matrix. For the way we're using it now, we're saying all identity matrices are square matrices. So, but A does not have to be square. So that's why but this this rule here is telling you the size of the identity matrix has to be when you multiply A by A. So if I have 1, 2, 3, 4, 5, 6, then I multiply. If I'm multiplying it on the left, I get a 3 by 3 matrix, and notice that will be. So I take this first row, multiply by this first column, and I'm going to have 1 times 1 plus 0 times 0 plus 0 times 0. I'm just going to end up with 1. And then this first row times that second column, I'm going to have 1 times 4, and then zeros otherwise, 4. And then the second row times the first column, everything's going to be 0 except for this 1 times that 2, so it's going to be 2. Second row, second column, everything's going to be 0 except for the 1 times the 5, so you get 5. You keep on going, you get the same matrix. But if I want an identity, or if I'm multiplying on the right side by an identity matrix, what I want to multiply by is a 2 by 2 matrix. So now 1 times 4 times, like this first first row, first column, I'm going to have the 1 times the 1, which will be 1, and then I'm going to have the 4 times the 0. So I get just the 1. 1 times the 4 times 0, 1, so 0. Then I'm going to end up with just the 4. 2, 5 times 1, 0. You don't really times, like dot product it. 2 times the 1 plus 5 times the 0. Just going to end up with the 2, and etc. You get the same thing out. So if A is m by n, then on the left-hand side you need an identity matrix of size m. Multiplying on the right-hand side, you need an identity matrix of size n. So, okay, here's the big warnings. It's not necessarily commutative. So A times B, if A and B are matrices, it's not necessarily true that B times A is the same as A times B. And if you pick 2 random matrices, they're probably not going to commute. So commute means that A times B is equal to B times A. Some do, and some don't. Like the identity matrix will commute if it's the right size. Right, if A is a square matrix, then A times I is equal to I times A. Or if the identity matrix is the right size. So the identity matrix commutes for square matrices, but and some other non-identity ones will, but it's not necessarily true in general. Excuse me. If A times B equals A times C, it does not necessarily imply that B equals C. It does, like if A has columns that are linearly independent, then A times B equaling A times C does imply that B equals C. So, and why does that make sense? Because then when you're B has columns that you're multiplying, that you're using as weights to combine the columns of A, and if they're linearly independent, then the point you're going to get, the vector you're going to end up with, we know will be unique. So it actually might be a little bit more than if they're square, for sure. And has that. I'll have to check and see if it's square. You need to have them square or not. I don't think so. But so notice here in the examples, these are not linearly independent columns, and so they're able to find two matrices that are not the same, to multiply by that, and the products are the same, but these matrices are not. And same thing with this. If A times B equals the zero matrix, then it doesn't imply that either A or B is zero. That's true for real numbers. But here you see an example where that's not true, but you may also notice, hey, these columns are linearly dependent. These columns are linearly dependent. If you have linearly independent columns again, then you would need to have the zero vector to get the zero matrix. I mean, you'd need to have the zero matrix. One of them would have to be the other one would have to be the zero matrix to get the zero matrix out. So, because by definition of linearly independent, if I have columns, so let me go back to my note page. If I have linearly independent columns and I multiply them by, I'm just going to stick with one matrix right now. So if I multiply them by anything, then, and get the zero matrix, so here I'm going to end up with, this is a 3 by 2, this is a 2 by 1, I'm going to end up with a 3 by 1. If I'm going to end up with a 3 by 1 matrix, well, what this says is x1 times 1, 2, 3 plus x2, 4, 5, 6 equals a zero vector, and so I have combinations of vectors that add up to a zero vector, and if these are linearly independent, then I know x1 and x2 have to be 0. Those coefficients have to be 0. So then I would know that this one would have to be a zero matrix also. So that's the reason. So that's where you start getting. I'll go back to this slide here. So where you start ending up with trouble is when these are not linear. These columns are not linearly independent. So, okay. Or if you know that the columns are linearly independent, then you do know something. You can make those conclusions. Okay. Quickly, properties of the matrix transpose. So the transpose of the matrix, so the transpose of this matrix is 1, 2, 3, 4. So the diagonals stay the same, and then you swap entries in a larger matrix. The transpose is going to equal 1, 4, 7. So this row here becomes the first column, and then 2, 5, 8, and 3, 6, 9. So that's what the transpose is. Transpose, it turns out doing some operations, it's nicer to use the transpose, or you end up needing to use the transpose. We're going to use transpose when we have a dot product that we want to rewrite as a matrix product. So we have two vectors, but we want to write it as a matrix multiplication, and then we actually have to end up using the transpose. So the transpose of the transpose is itself pretty straightforward, because when you take the transpose, the 3 is going to move up there, but then you take the transpose again, and the 3 is going to move back. Anything that moves back and moves in the transpose is going to move back when you take the second transpose. A plus B transpose is A transpose plus B transpose. You can convince yourself if you write out some general matrices to do that. Doesn't change the scalar multiplication, because R times A is just going to get R times all of your entries, R, and then when you transpose it, you're still going to have R times all those entries, and you could factor out an R from all those, and you just have R times A transpose. Now this one is the tricky one. Why is A B transpose equal to B transpose A transpose? Notice the order changed, okay? It's not just A transpose B transpose. You can convince yourself by doing an example. Okay, we're going to go explore this. I just wrote out an example to save us some time on another page. But before we jump there, I'll touch on these. So if A is a square matrix, then A plus A transpose is a symmetric matrix. And for any matrix A, the matrices A transpose A and A transpose are symmetric matrices. Symmetric matrices have really nice properties. We're going to bump into some of those properties and use them. And these are times when you always get symmetric matrices. And to convince yourself, write out an arbitrary A, and then you can write out the arbitrary A transpose, and you can even just a 2 by 2, and you can convince yourself that those are true. But let's go back to this one. So I went over here to the notes page, wrote out some things. We have an A times a B transpose, and I'm going to transpose that whole thing. So I do the product first, and then I can transpose the product. And the product, I'll take like the 1 and the -3, and then multiply it by this column to get my -4. 1 times a -1 plus a -3 times 1. So notice this needs to match up with that. That matches up with that. And we're going to come back to that when we try to make sense of this. So 1 times a -3 times 2 times a -4, it gets us 2 plus 12, which is our 14 over here. And then we can transpose that to get a -4, 2, 14, and a -12. If you think, well, maybe that should just be A transpose B transpose. So I wrote down A transpose B transpose down here. And then our first entry is 1 times 2 times a -1, 2. And that is 3. And that's not the same as the -4 we have there. So this isn't making sense. But if you switch the order, then you get this -1, 1 times a 1 -3. And those were exactly the columns and rows that we were taking as the dot products to get our entry over here. And over there. And so the thing is that this column has become the row, and this row has become the column. And if we switch the order, then we get to match those up in our products, and then we'll end up back with the right values here, because the corresponding dot products that we did, like for example, to get the -12, that was 2, 4 times 2 a -4. Well, here we have the 2 -4 as the row and 2, 4 as the column, and it'll still go down in that lower right hand corner. So, so this is one to be careful of. So if you see an A/B transpose where you're solving a system or solving an equation, yeah, you want to make sure that you want to make sure you don't do that. You need to switch the order. So, okay, thanks.